Hello, welcome to another video on apply electricity. So I'm going to continue to solve last year paper. That is apply electricity first semester 2023-2024 promotion. Okay, or 2023-2024 academic year, right? Okay, so we stopped at question 61. Okay, so I'll continue from question 61, then solve up to question 90. Okay, so we are going to be solving 30 questions as usual. Now starting with question 61. Okay, question 61. Now question 61 here. Okay. A combination of 4 capacitors shown in figure 3. Find the value of C to obtain an equivalent capacitance of 0.5 microfarad. So we have figure 3 here. Okay. So with figure 3, you can see we have 4 capacitors, right? We have 4 capacitors. Now the overall equivalent capacitance for this is going to be equals to 0.5 microfarad. So based on this, what this just trying to say is to find the equivalent capacitance. This is equals to, then based on that we can use that to find the capacitance C. So to do this, we are going to find the equivalent capacitance step by step. So let's start with the 6, the capacitor C, which is in parallel with 0.6 microfarad, right? So let's get the equivalent capacitance there. So that part, the equivalent capacitance for C, 6 microfarad capacitor, is going to be equals to, because they are in parallel, so that will be capacitance C here plus 0.6 micro. Now you can see that after that, I have now my equivalent, which is C plus 0.6 micro here. Okay, it's now going to be in series with the 0.2 microfarad and then 0.8. So you get that part to the equivalent capacitance. Since they are in parallel, so we are just using we add them, right? That will be 0.2 plus 0.8. So it will give me 1 microfarad. So we have this, and these are now in series, right? So that means that now we can get the equivalent capacitance, which will be the overall equivalent capacitance for this. Since they are in series, we take their product, right? So the whole of this is my capacitor here. So C plus 0.6 microfarad times 1 micro all over. Then we do the sum, right? Their product of the other sum. So C 0.6 micro, which is the whole of this, then plus 1 micro, and then this will be equals to the equivalent overall equivalent capacitance, which is 0.5. so this will be equals to 0.5 micro. Now you can simplify with this, so you multiply both sides here by 1 micro, so that will be C micro, and then this 0.6 times micro, that was 0.6 micro square. Then you multiply this by this, so this is what, 0.5, okay, micro C, then plus 0.6 times 0.5, 0.6 times 0.5, that gives me 0.3, I mean micro, right? Micro, then 0.5 times 1 here, micro, that was 0.5 micro square, here to micro square. Now we group like terms, so meaning 0.5 here, you bring it here, so that we get 1, okay, so that we get here to be micro C here. Here will become minus, right? Minus 0.5 micro C, another C here. So that's, these ones are gone. Then you take this one micro, 0.6 micro square across, so that we get here to be 0.3 micro square plus, right, 0.5 micro square then you send this out with minus 0.6 square. So when you do this, you get here to be what, 0.5 micro C, then that will be sum of this 0.3 plus 0.5, 0.8 minus 0.6, that will be 0.2 micro. So you divide by this, you get 0. Remember a square, 0.2 micro square over 0.5. So that will give us 0.2 divided by 0.5, 0.4. So this leaving 1 micro, that will be 0.4 microfarad. So this is one way of doing it, right? So you can do it this way and you get the answer. But there are other several ways you may choose to answer this. But just probably, if there is time, you just pick the value and then you place it and see if you get 0.5. The one that will give you the 0.5 becomes the answer. Okay. Now moving to question 62. Obtain an expression for the energy stored in a capacitor C in terms of the charge on it. So this is first one was question 61. So here is 62. You have to now express the energy stored in a capacitor, the formula in terms of the charge on it. So if you look at the formula, it's half the capacitance times what? Voltage square, right? We want to express this in terms of charge. We know that charge, right, on a capacitor is going to be equal to the capacitance, right, times the voltage, right? So here we make charge voltage the subject, so that we get here to be voltage will be equals to charge over capacitance. So that we replace the what, in place of the voltage we replace, right, this formula. So here now we have the capacitance, then now the voltage place, now we replace charge over what, capacitance square. So this is going to be equals to half to C. It will now be what, Q square, right, over C square, capacitance square. So this is going to give us charge square 2C. So the answer here becomes what? B. Now moving to question 63. Dielectric materials and capacitors increase. Okay, so this question here, if we have dielectric in a material, we know that when it comes to designing a capacitor, capacitance is equal to what? The dielectric material, right? Times that's the absolute permittivity times area divided by the distance between them. So you can see that the absolute permittivity here is what? Relative permittivity times permittivity of free space, mean times area over D. So you can see the capacitance here is directly proportional to the what? The relative permittivity of the material, which is a dielectric, right? So if you increase the dielectric, meaning you are increasing the capacitance, and capacitance is an insulating material. Okay. Now, so capacitor increasing the dielectric material capacitors, in capacitor increase the capacitance. So now B, resistivity. Now when it comes to resistivity, again we are dealing with insulating material. So if you are playing insulating material where there are charges, right, it's going to increase resistivity. So the answer for this is what? B. Is C, which is both capacitance and resistivity will increase. Once you have a dielectric material, you have both capacitance and resistivity increasing. So the answer here becomes C. Now question 64. Capacitor obeys thus: A. Coulomb's law, B. Ohm's law, C. Both Ohm's law and Coulomb's law, D. None of these. Okay. So if you look well, the answer here is going to be A. Why? Because when it comes to Coulomb's law, we apply Coulomb's law when we are dealing with charges, right? If you have two charges and you want to find the force between those two charges, that's when you use Coulomb's law. So if you're having capacitors, they tend to store charges. So once you have charges, the law that is going to be useful there is going to be Coulomb's law. So the answer here is A. Now moving to question 65. So 64, then 65. The voltage across two capacitors C1 and C2 connected in series are 4 volts and 2 volts respectively. When the combination is connected across a 6 volt source, a 2 microfarad capacitor is now connected across C1 and the voltage now measured across C2 is 3 volts, as shown in figure 4A and then 4B. Evaluate C1 and C2. Okay, so this question is kind of long, but we will focus on the figures, right? You can see if you look at figure 4A that we have here, this will be 4A, right? You see that on top of what C1 we have 4 volts. On top of C2 we have also what? 2 volts. I mean that's the voltages across the capacitors. And then we have the voltage supply to be 6 volts, right? And then you look at question figure 4B. We now have C1 in parallel with what? 2 microfarad capacitor, and then they are in series with what? C2. Okay, now we have to find C1 and C2. That's what this question is all about. So you can see that by looking at this, for each figure that we are giving, I think we will get an equation out of it, right? So we have one equation from 4A, another equation from 4B. Since we are having two variables, that will allow us to what? To able to calculate for the what? The two variables, meaning C1 and C2. So let's start with 4A. We try and drive an equation out of it. So since C1 and you can see C1 and C2 are in series, so mean the charge, as we know, is going to be the same. The charge on what? C1 and C2, they are going to be the same. Let's say I have C1 is having charge 1, right? meaning Q1, and then C2 I have charge 2. What we are saying that since they are in series, meaning charge 1 here will be equals to what? Charge 2. The same charge is going to be on them. Now we can get charge 1, right? We know that we can get charge 1 by using this formula. Charge, which is always equals to capacitance times what? Voltage. So meaning C1 times V1 will give me charge 1. And then charge 2 will also be what? C2 times what? V2, right? So with this charge 1 here will be equals to, here is just C1. We have the voltage that across C1 is what? 4. So I can write this will be what? 4 C1. Now when it comes to charge 2, right, it's also going to be equal to the voltage across is 2 volts, so that will be what? 2 C2. Now I can equate them, right? So I know charge 1 is equal to charge 2, meaning I can write 4 C1 will be equal to what? 2 C2. We divide both sides by 2 so that we get 2 C1 is equals to 1 C2. So I can label this as equation 1. So 2 I can label this equation 1, which is C2 equals to C1, equation 1. Now we go to the next figure 4b. Okay, now I get another equation out of it. So if you look at this figure, we can make use of what? Similar case, right? But this time we can see that we don't know the distance. We are given the voltage source to be what? The total voltage to be what? 6 volts, and then we have on C2 we have 3 volts, right? So that means that we know that in that case, let's say here is V2, right? Then on C1 we have V1, right? So that means the total voltage should be equals the sum of V1 and V2, right? So 6 volts here should be equals to V1 plus V2. And you can see that V2 here is 3, so I can just have V1 plus 3. So we can get V1 to be what? 6 minus 3. That will give us 3 volts as well. So V1 is what? 3 volts. Once we know this, we can now look at what? The 2 microfarad capacitor and then the C1 in parallel. So since they are in parallel, I mean they have the same voltage. Now the voltage across the 2 microfarad is now also what? 3 volts. So I can get the charge that is on this one, right? So the charge on 2 microfarad capacitor here is going to be equal to what? The voltage, which is V1, over what? Times, right? So 8 capacitance, which is 2 microfarad. So here is going to be 2 times 10 to the power minus 6 times what? The voltage, which is 3. So this is going to give me charge on, so we want 6, right? 6 microcoulombs for the charge on the 2 microfarad capacitor. Now that we've gotten, we can see that when it comes to the charge now, we can have total charge, right? QT for this one. because we have a junction here, because 2 microfarad capacitor and then C1 are in parallel. So the total charge here will be equal to what? Charge that is on C1 plus what? Charge that is on 2 microfarad capacitor. Okay, you get this. Now with this, you can see that the total charge here is going to be the same as the charge on what? C2, right? Because C2 is just, there's no any parallel element there. So I can write total charge here equals to what? Charge on C2, which is going to be equals to its capacitance C2 times its voltage V2. That will now be what? 3C2. So I can write here 3C2 is equals to Q1 plus, this is now what? 6 microfarad. So now I can also find Q1, right? In terms of its capacitance and voltage. So which will be, the voltage as we know is 3, right? So that will be 3, its capacitance C1. So we have this. Once I've gotten this, you can see now I can label this as what? My second equation. This is our second equation. So if you look at equation 1 that I have and equation 2, I can now simplify and get one of the variables. So let's say here I have C2 is equals to 2C1. So meaning I'm going to replace what? 2C. Okay. Let me look at this. C is equals to what? 2C1. So the place of C2. So here let me replace there to be C2, and now I'm going to put there C1. Okay. So have C1. Here we got so now I'm going to have 2, right? 2 C1 equals to 3 C as this. So here will be what? 6 C1 equals to 3 C1 plus this. Now that I can even divide both sides by 1. Here's micro. Can bring this one here, so we can have this. So this will see 6C1 minus 3C1, that will just be what? 3C1, which is equals to 6 micro. Now C1 going to be equals to 6 micro over 3. C1 becomes what? 2 micro, which is now 2 microfarad, right? Once you get in, you can get C2. We know C2 is twice of what? C1, based on this formula. So C2 will now be equals to times 2 micro. So that will be 4 microfarad. So the answer here is what? A. Okay. So you see that we get C1 to be 2 microfarad and then C2 to be 4 microfarad. Now question 6A. Question 66 rather. So 66. What is the equivalent capacitance at the terminal AB. So this terminal AB is here. These are my terminals. What is the equivalent capacitance at the terminal AB of the circuit shown in figure 5? So this is figure 5. We are just to find the equivalent capacitance. So here we are going to start on the right hand side. So you can see that we have 15 microfarad is what? In series with what? With 6 microfarad. So we get the equivalent capacitance. Since they are in series, the equivalent capacitance for 15 micro and then 6 microfarad here, they are going to be equals to their product. You take their product, 15 micro times 6 micro, then over the sum, 15 micro plus 6 micro. So the equivalent capacitance for 15 microfarad and 6 microfarad becomes, so we take their pro, so meaning 15 times 6, that is going to give me 90 over their sum, which is 15 plus 6. Okay, so we get here to be 4.286 microfarad. Okay, now once I've gotten this right, you can see now I can even come and replace here this place which I've gotten is now just the equivalent capacitance here. So when I come here, then I have the terminal A and B. So you can see now my value here, which is 4.286 microfarad, is now in parallel with what? 50 microfarad here. So again, we get the equivalent capacitance. Okay, but this time I now have my 15 microfarad capacitor here being parallel with what? 4.286 microfarad capacitor. So the equivalent capacitance there becomes, so here we just do the sum because they are in parallel, so plus 15, so that will be 19.286 microfarad. So we gotten this part. Now we move ahead with this. Now I've calculated for this part. Now I left with the last part, right? Which is this one here, the equivalent capacitance. You see that it's going to be in series. I don't have to sketch this. It's going to be in series with what? 15 microfarad capacitor. So that means now the overall equivalent capacitance which we are asked to find is going to be equals to 15 microfarad times 19.286 microfarad capacitor over their sum, 15 micro plus 19.286 micro. So this is going to give me this times 15 divided by 15 plus 19.286. So here I'm going to get 8.44 microfarad. So when you check here, the answer is how is going to be what? B. Okay, so we get here to be B. Question 66 to be B. Now moving to question 67. Okay. Question 67. A 40 microfarad capacitor is charged to store 0.2 joules energy. An uncharged 60 microfarad capacitor is then connected in parallel with 40 microfarad through perfectly connecting leads. What is the voltage of the parallel connection? So looking at this question, first you can see that you have a capacitor and it's being charged, right? And the energy that is stored in the charge is 0.2 joules, right? So then after that, an uncharged 60 microfarad capacitor is then connected in parallel with the 40 microfarad through perfectly connecting leads. What is the voltage of the parallel connection? So what this means is that we look at this, right, in this way, right? If first we have a capacitor, I have which is 40 microfarad. Now this one is being charged, so it's being charged to a certain energy. So let's get the charge first. So what is going to be the charge here? To get the charge for this, I can write energy. Energy is going to be equals to half capacitance times the voltage square. So let's get the voltage. Then after that we get the charge. You can even see that here I can just go and even use the formula that we derived, right? I can go and use that formula we derived, and then I just get the charge straightforward, right? Get the charge straight. But I'm not going to do it this way. So let's get the voltage first. So if we make voltage the subject, we get V will be equals to voltage equals 2E divided by the capacitance square root of that. So here I'm going to replace the values. So we have 2 times what? The energy is 0.2, then divided by the capacitance, which is 40 microfarad. So this is the, and then let me see, what do I get? So I'm going to get 2 times 0.2, which is 0.4, divided by 40 times 10 to the power minus 6. So the square root of this, I'm going to get 100. This is voltage that we are calculating. So I'm going to get 100 volts for this, right? 100 volts. So for this, the voltage here across this is going to 100 volts. Now let's get the charge. So what is going to be the charge? Because the charge is going to remain the same, right? When you now bring another capacitor, right, in parallel with the first capacitor that we are given. So the charge is equals to capacitance times voltage. So the capacitance, which is 40 times 10 to the power minus 6 times 100, that is going to give us, okay, this one. So that would just be 4 millicoulombs, right, for the charge. Now, if from the question here, an uncharged 60 microfarad capacitor is then connected in parallel with the 40 microfarad. So if you connect another one now. All right, so now that I have this, I have my 40 micro. So now we connect a 60 micro here, and then they are in parallel, right? Meaning they are now in parallel this way, for example. Now that are in parallel, but the charge, right? Remember the charge here is still going to be the same, right? So the charge here is still going to be. So you can see now the voltage. We asked now to find the voltage across this part. We have to find the voltage across here. This is what we are interested in. Now, since the charge is going to be what the same, conservation of energy, the charge that we got for the first case, right, with the what, with the energy is going to remain. So the charge here, 4 microcoulombs here, is going to be here, the total charge for this. Okay, that will be the total charge. Now that we know that, so to get the what, the voltage across the two resistors which are connected in parallel, so the voltage is going to be equals to the equivalent capacitance times what, the total charge, which is the one that we just calculated. No, I'm writing the formula wrongly. It's rather what, the voltage will be equal to voltage here will be equals to the total charge divided by the one equivalent capacitance. Okay, so this is going to be, so we know the total charge, which is 4 milliseconds. Now the equivalent capacitance is what we have to get. So equivalent capacitance for this, for these two capacitors, is just going to be their product. So 40 micro times 60 micro divided by 40 micro plus what, 60 micro. So the equivalent capacitance for this becomes 60 by 40 divided by 60 plus 40, which is just 100. So we get 24 microfarad for this. Now my voltage, the voltage across the capacitor that are in parallel is going to be the charge, which is 4 milli, meaning 4 times 10 to the power minus 3 over 24 micro, 24 times 10 to the power minus 6. So with this here is send this here with what, you bring this up, right? That'll be 1 over 6, right? 24 divided 24 divided by 4 is what, 6, right? So here we 1 over 6 times 10 to the power, you bring this up, that is 10 to the power, that will be 3 now. So inverse of 6 is going to be what? Inverse of 6, that is going to give us so here we got this thing to be, I get 4, this in 4, my here was what, 40 times this, yeah, so that's 4 milli, that is correct. Okay, 4 milli here, Okay, so 40, I'm just trying to cross check here. 40 times 60, so that will be 24. So here I'm having 4 times 10 to the power minus 3 divided by the equivalent capacitance, which is what? 24 times 10 to the power minus 6. Okay. So what am I getting? So here the answer, what is the voltage on the parallel connection? So with this here, in the, where am I? Okay, looking at, I think there is a mistake somewhere. It's here. This part here that they are in parallel, so we do the sum. I don't know why I take the product. So you have to be careful with this so that you don't repeat these kind of mistakes. So here they are what? They are in parallel, right? So meaning the equivalent capacitance for this is equals to be the sum, meaning 40 micro plus what? 16 micro, which is going to be 100 microfarad. So that when we come here, we get the charge, which is 40 milli, then over 100 micro. So this becomes the voltage here now becomes, this will cancel. Okay. So here we come 10 to the power. Okay, let me just use my, okay, this one we can 10 to the power 3. Now I have 4 here is 0.4, so that will be what? 40. So we get 40 volts. So the answer for question 67 is what? 40. Now moving to question 68. A set of parallel capacitors are connected in series with 300 microfarad and 100 microfarad capacitors. The parallel capacitors are 200 microfarad, 50 microfarad, and 150 microfarad. Determine the equivalent capacitance of the series parallel combination as shown in figure. What is just saying that we have 2 microfarad, 200 microfarad, 50 microfarad, and 150. They are connected in parallel, and then in series with what? With 300 microfarad and then 100 microfarad capacitors. So to find here, question 68, to find the equivalent capacitors, again, we start with what? The capacitors which are connected in parallel. So we just add them. So you can see that the equivalent capacitance there, let's say for the parallel connection part, so that will just be 200 micro plus 50, then plus 150 micro. So that will give us 400, right? 400 microfarad. Now you can see that after that, this part is now going to be in series, right? It's going to be in series with this. So I can sketch here. This is 400 microfarad. It's now going to be in series with 300 micro, and with the next one, which is 100. And once these are in series, we now get the equivalent capacitors. So to get this, since there are 3, I'm going to write the equivalent capacitance here, or what? Equivalent capacitance. Inverse or reciprocal of the equivalent capacitor equals to 1 over C1 plus 1 over C2 plus 1 over what? C3. So here you use your calculator, you do the sum of the inverses. After that, you invert the final decision, right? You inverse the final answer, that will give you the equivalent straightforward. So if not, if you try to do the other way around, you are going to spend a lot of time. So here I'm having what? I'll take 400, inverse of that, 400, inverse plus 300, inverse plus 100, right? Inverse, then inverse the final answer. So when you do that, you get 63 point. So it's equivalent capacitance of this. We give you 63.1, let's say 16 microfarad. So that will give me what? B. Moving to question 69. The relative permittivity is defined as, so when you talk about relative permittivity, we can define it as what? We know that absolute permittivity, right, is equal to relative permittivity times the permittivity of what? Free space. So that means by the product, we can now make this to be the subject. So relative permittivity can be defined as the absolute permittivity divided by the what? The permittivity of free space. Right? That's one way. Another way we can define it in terms of this formula, which is in terms of the electric flux density is equals to what? The absolute permittivity, which is the same as relative permittivity times the permittivity of free space. So you can see that relative permittivity can be equal to what? The electric flux density, right, divided by the product of what? Electric field intensity, then times the permeability of free space. So this is another way you can define this. So when you look at the possible answers here, you can the relative permittivity is defined as the electric field strength divided by the electric flux density. You can see that this is wrong, right? So here is wrong. B, electric flux density divided by electric field strength. Okay, we have electric flux density, but also divided by what? The permittivity of free space. So this one is wrong. Then C, electric flux density divided by dielectric field strength. Okay, dielectric field strength is just referring to what? The electric field strength. So it's just the same as B. So the answer is none of them. Is D. None of this clearly define the relative permittivity. Now, question 70. What is the standard unit of electric charge? So the standard is coulombs. Question 71. 1000 picofarad is equals to, so if you are having 1000 pico, So that will be 1000. So you can see the other ones, they are in terms of nano, right? So here we just 1000. That means 1 times 10 to the power 3 times 10 to the power minus 12. So that will be what? 1 times 10 to the power minus 9, which is 1 nanofarad. So the answer becomes A, 1 nanofarad. That is the same as 1000 picofarad. Now moving to question 62. A 100 battery is connected across the terminals AB of the circuit of figure 7. Determine the equivalent capacitance. So here again we have to find the equivalent capacitance for question 72. So with this, you can see that if you look up, you see here up here is 650 nanofarad. But when you look at the rest of what the capacitors, they are expressed in micro. So we change this one to also be in micro. So 65 nanofarad in pico, meaning you move what, and then in micro you move this in 3 times, right, the decimal. So we have, it's now going to be 1 2 3. So that will be 0.65. So then we get microfarad. So we get this. Now that we got 0.65 microfarad, now we can try and get the equivalent capacitance. And we start with what, the parallel connection part. So we have now 0.65 micro is in parallel with what, 0.75 microfarad. So that will give us the equivalent capacitance for these two, 0.65 microfarad, and then the 0.75 is going to give us just the sum, right? So now 0.65 plus 0.75. So that gives me 1.4 microfarad. Now that we've gotten this, you realize that after this, right, we've gotten the whole of this part. When you replace it, all these three are going to be in series, right? 10 microfarad is going to be in series with what here, which is 1.4 microfarad. So to get the equivalent capacitance, again we just take the equivalent, overall equivalent capacitance of what, the 1 over what, C1 plus 1 over C2 plus 1 over what, C3, which is 1 over 1.4 micro plus 1 over 10 micro plus 1 over what, 5 micro. So here 1 over equivalent capacitance, and this is going to give me, okay, so we do this. So I'm just going, since they are all in micro, so it's been, so we just get 1.5 inverse plus 10 inverse plus 5 inverse. Then we inverse our lesson. So this is going to give me, answer here is 9. I got 0.986. So this the micro, right? Remember, this will be a micro. This is the answer. So you can see now the possible answers. We have A 900 nanofarad, B 800 nanofarad, C 980 86 nanofarad, and then D 950 nanofarad. So we express this in nanofarad as well, meaning you move this, so you have 986 times 10 to the power minus 3 times 10 to the power minus 6. So that is going to give us 986 nanofarad. So we get this. So the answer here becomes C. Now moving to question 73. In figure 8, P, Q, and R are identical capacitors, and the total equivalent capacitance of the circuit is 3 microfarad. What is the value of P? So this is just taken from the handout, right? I think we solved this even in class. So, but I'm going to solve it very fast. So here again, the overall equivalent capacitance is 3 microfarad. So we start with what? The first part here. I think I have to speed up. So 3.5 and then 4.5 are in parallel. So we add that part up. So we get here to be 3.5. That will be 8, right? So we get there to be 8 micro. 8. And you can see that 8 is going to be in series with 2 micro. So I get the equivalent capacitance for 2 micro and 8 micro here to be 2 micro times 8 over 2 micro plus 8 micro. So that part, we'll be done with that part, so that we get here to be 2 times 8. Then the sum mean divided by 10, that will be 1.6. So here is 1.6 microfarad. Now, this 1.6 here is going to be in parallel with what? This circuit diagram here that we have. So here's my 1.6. And then we have here P, Q, R. But we are being told that what is the value of P, right? And we are told that they are identical. So these are identical, meaning they have the same capacitance. So let's say the capacitance P, Q, and R, they are all the same. So let's say the capacitance is C, so equals to C. So each of these, the capacitance is C. This is just labeling. So because of that, the equivalent capacitance for the down part, right, this part here, meaning the PQ and then R, is going to be, since they are identical, means it's going to be what? And they are in series. We take the capacitance over the number, and there are 3. PQR, there are 3 in number, so over 3. This will be the equivalent. Now that we've gotten this, we can now see that 1.6 microfarad capacitor here is now going to be in parallel with what? This part. Okay. And then this what will give you the overall equivalent capacitance, which is giving us what? 3 microfarad from the question. So that simply means that the sum should be equal to 3 microfarad. So 1.6 micro plus C over 3 micro. So here give us, we multiply by 3. So 3 times 1.6, 4.8 plus C, right? And here to be times 9, right? Now my C is equals to times minus 1 plus 9. So you get this to be equals to what? 4.2 microfarad. So our answer for this is what? 4.2, which is D. Now moving to what? 74. The dash capacitor is a polarized capacitor. So polarized one, we talk about electrolytic one capacitor. That one is polarized, so you have to be careful with the polarity. Now moving to question 75. The charge storage determinant of a capacitor is, so this is just to say the charge, right? Storage determinant of a capacitor. You know the charge that is going to be stored in a capacitor depends on what? Electrode area and dielectric. Electrode area here is talking about the area of the plate, right? Then we have the microstructure of electrode and electrolyte. Thermodynamics and mass, then none of this. So the answer here becomes A, right? The electrode area means talking about the area of the plate, and the dielectric that we have, right? So here becomes A. Question 76. When capacitors are connected in series, then that remains the same. So when we have capacitors, they are connected in series, like we just saw. Let's say, for example, the charge on them is the same, right? So let's say this charge is the same. But when you come to the voltage across them is different. So V1, V2, they are different. So, or it varies. So with this, the answer here is going to be what? Here, the charge remains the same and the voltage varies. So the answer here will be A. Okay. Moving to question 77. 3 capacitors, 50 microfarads, 25 microfarads, and then 40 microfarads are connected in parallel across a 250 volt supply. Find the total energy stored. So here, to find the total energy, since we are talking about 3 capacitors and they are connected in parallel, this is question 77. So 3 of this, they are connected in parallel. So this, and then across a voltage supply, meaning you connect this to a voltage source, which is 240 volts. So that means that to find the total energy stored, meaning we get the equivalent capacitance, right, for this that are connected for this capacitor, and the equivalent capacitance is going to be equals to, since they are in parallel, it's just going to be the sum. So this is 15 micro. The next one is 25 microfarad. Then the last one is 40 microfarad. So we just do the sum. That will be 15 micro plus 25 plus 40 micro. So that is going to give me 15 plus 25 plus 40. So I get here to be 80 microfarad. Now with this, so I've gotten the equivalent capacitance. So now let's get the energy stored. Energy stored is going to be equals to half the capacitance times what? The voltage square, meaning the voltage supply. So the capacitance here is the equivalent capacitance. So I'm just going to replace the values, meaning half times 80 micro, right? 10 to the power minus 6. Then the voltage square, which is 250 square. So that will give me 80 times 10 to the power times 10 to the power minus 6 divided by 2 times 250 square. So that will be 2.5 joules. So the answer here becomes C. Okay. Now moving to question 78. What happens to the potential difference between capacitor plates as the distance between them is double, right? So if we have the potential difference between two as a distance, we know that question 78, we know that electric field strength is going to be equals to voltage over what? The distance between the plate. So when you make this, you know that voltage is going to be what? Directly proportional to the distance between the plates, right? The voltage will rather be. So if you are doubling the distance, so meaning you are doubling the voltage as well. So meaning the voltage is also increasing. So if you are increasing the distance between the plate, you are also increasing the voltage. So the answer here becomes B, right? So A is decreased, B is increased, C is remain the same, and then D is none of this. So the answer is B. 79. Determine the equivalent capacitance of the following series connected capacitors. So here, okay, we just have 4 capacitors, meaning 2 microfarad, 80 microfarad, 60 microfarad, and then 140 microfarad. They are connected in series, so you have to find the equivalent capacitance. So this one, you just use your calculator, and this becomes very easy. So I get 1 over 2 micro plus 1 over 18 micro plus 1 over 60 micro plus 1 over 140 micro. So I will just take 2 inverse plus 18 plus 60 plus 140. Then after that, take the inverse. So that will be 1.7. Here with this equivalent capacitance, you get 1.73 microfarad. So the answer here becomes C. Okay. Now moving to question 80. A 3300 picofarad capacitor is required to store 0.5 joules of energy. Find the potential difference to which the capacitor must be charged. Again, this question is also lifted straight from the handout, right? We even solve it in class. So question 80, we are given the energy, right? Then we are given the capacitor, the capacitance, and you are asked to find the voltage. So the same energy formula, but you make this time energy the subject. The voltage the subject. Then you calculate for the voltage, which is the potential difference. So energy, which is equals to, I think I even wrote this formula, right? So let me write it straightforward. The voltage is going to be equals to square root of 2E over what? C. So with this, I have 2 times what's the NA, which is 0.5 milli. Then you divide it by the capacitance, which is 3300 pico to power minus 12. And when you do this, you get what? The answer to be 500, right? 550 rather, 0.50 volts. So you get the answer here to be what? A. So the answer for this is A. 81. 2 parallel rectangular plates measuring 20 centimeters by 40 centimeters carry an electric charge of 0.2 microcoulombs. Calculate the electric flux density. So this one, question 81, is about electric flux density. We know that electric flux density, we use D, is equals to what? The charge over what? The area. So you can see here that we are given the what? The dimensions, right, of the plate. So we have 20 millimeters, 20 centimeters by 40 centimeters. So that will give us the area. So in the area part, I can just write 20 centimeters, which is 20 times 10 to the power minus 2. Then times what? 40 centimeters, meaning 40 times 10 to the power minus 2 as well. Then the charge, which is given as 0.2 micro, meaning 0.2 times 10 to the power minus 6. So you solve for this and this will give you your answer. So to get this, we get 0.2 times 10 to the power minus 6, then divided by 20 times 40 times 10 to the power minus 4. So we get here to be 2.5 micro. 2.5 micro. The charge, which is coulombs per meter square. So where is question 81? So the answer here becomes D. Okay. Now question 82. A capacitor consists of two metal plates, each of area 50 centimeters square and space 0.2 millimeters apart in air, is connected across a 120 volt supply. Calculate the potential gradient. Potential gradient is the same as what? The electric field strength, which is E, right? Which is E. So to find the potential gradient here, we are given the voltage. So meaning E is equal to what? The voltage over what? The distance between the plates. The voltage here is given as 120, and the distance or the space, right? The distance between the plates is 0.2 millimeters. So means 0.2 times 10 to the power minus 3. So this becomes 120 divided by 0.2 times 10 to the power minus 3. So we end up getting the answer here to be 600,000, which is 600 kilo 600 kilo volts per meter. So the answer here becomes 600 kilo, which is D. Now moving to 83. Calculate the capacitance of a parallel plate capacitor having 5 plates, each 30 millimeters by 20 millimeters, and separated by a dielectric 0.75 millimeters thick, having a relative permittivity of 2.3. So this question, I think even this question is also from the handout. It's probably, it's also lifted straight from the handout. Now to find we have to find the capacitance, right, of a parallel plate. So here we are given the number of plates. So we have to use this formula. Question 83. We use capacitance, this formula, capacitance will equal to what? The absolute permeability times what? Area over the distance between the plates. And then since we are having a number of plates here, right? So through interleaving, so that will be n minus 1 as well. So now this, you can further expand on this. Capacitance equals to the absolute permittivity here, what? Relative permittivity times the permittivity of free space times area over the distance between the plates, then times the number of capacitors through interleaving. So we have this formula. Now you just replace the values, right? Here let me write this down. So the relative permittivity is 2.3. The permittivity of free space is a constant value, right? Which is 8.854 times 10 to the power minus 12. Now, once I've gotten it, now the area, you look at the dimension that are given. We have 30 millimeters by 20 millimeters, right? So that is going to what? 30 times 10 to the power minus 3 times 20 times 10 to the power minus 3, then times the number of then n minus 1. So that will be n here is 5, right? The number of plates there are 5, so 5 minus 1. Then you divide by the distance between them, which is 0.75 millimeters. So 0.75 times 10 to the power minus 3. So this one is also from the handout, because I remember solving this kind of question in class. So we have 2.3 times 8.854 times 10 to the power minus 12 times 30 times 20 times 10 to the power, that will be minus 6 times 4. So we get this divided by 0.75 times 10 to the power minus 3. So we get this answer to be 66.517 times 10 to the power minus 11. So we express this. When you look at the possible answers here, you can see that question 83, they are expressed in pico, right? So to make this pico, that means you move to the right. So 65.17 times 10 to the power minus 1 times 10 to the power minus 11. So that will be 65.17 picofarad. So the answer here for this becomes B. Okay. Now moving to question 84. A 19 plate 50 millimeters by 300 by 30 millimeters parallel plate capacitor has capacitance of 1000 picofarad and each separated by dielectric thickness 0.4 millimeters. What is the relative permittivity of the dielectric? Again, this one also seems to be lifted from the handout, straightforward. So this time you can see it's the same formula that we use here, right? This same formula, but this time we are given the capacitance, but we are now being asked to find the relative permittivity of the dielectric. So meaning we make the relative permittivity here the subject in this formula. So I have 84, question 84. So let's make this the subject. So when you make it, you get what? To be equals to, meaning you multiply by capacitance and the distance between the plate. Now you divide by permittivity of free space, divide by area, then divide by the number of plates minus 1, n minus 1. So this becomes the formula. So again, it's just replacement again. So the capacitance here is now giving us 1000 picofarad, 1000 times 10 to the power minus 6. Then the distance between the plates is 0.4 millimeters, means 0.4 times 10 to the power minus 3. Now divided by permittivity of free space, which is 8.854 times 10 to the power minus 12 times the area. The area here, you can see this time the area of the plate is given. The dimensions are 50 millimeters by 30 millimeters, right? So that would just be what, 50 millimeters, meaning 50 times 10 to the power minus 3 times 30 times 10 to the power minus 3. Once I've gotten this, now the number of plates, which are 19. So 19 here minus 1, that will be 18. So now let's see what we get. So the first one, 1000 times 10 to the power minus 6 times 0.4 times 10 to the power minus 3. Okay, so we got the first part here, divided by 8.854 times 10 to the power minus 12 times 50 times 30 times 10 to the power minus 6 times 118. Okay, so we have this. Now our answer here. Okay, the answer that I'm getting is, if I look at the possible answers, I think let me do my, I'm getting very huge numbers, so let me go over this again. Again, the capacitance here, let me check the formula. So everything, yeah, everything's okay. So let me read this one. Again, the capacitance is giving us 1000 pico, ten to the power minus 12. It's again as pico. Why am I writing this? So pico times 0.4 times 10 to the power minus 3. Okay. Divided by 8.854 times 10 to the power minus 12 times 50 times 30. Right? So we have times 30 times 10 to the power minus 6 times 18. So we have this. Okay, so I've gotten it now. It become 1.67. So we get 1.67. So the answer here is A. Moving to question 85. The charge on a plate of capacitor is 6 millicoulombs when the potential between them is 2.4 kilovolts. Determine the capacitance of what? The capacitor. So question 85. We have been told that the charge on a plate is what? Okay. Now we have to find the capacitance. Capacitance is just going to be equal, again, charge is equals capacitance and voltage, which means capacitance equals to charge over what? Voltage. Right? So capacitance now is going to be the charge, which is giving us 6 millicoulombs over the voltage, which is 2.4 kilo. So this is going to give me, okay, we are just going to have 6 times 10 to the power minus 3 divided by 2.4 times 10 to the power 3. So that will give me 2.5 2.5 times 10 to the power minus 6 farad, which is 2.5 microfarad. So the answer here is 2.5. Now question 8 says a capacitor uses a dielectric 0.4 millimeter stick and operates at 30 kilovolts. What is the electric field strength across the dielectric at this voltage? So this question was given as a bonus because the answers, it's supposed to have expressed in mega, right? But they were expressed in then kilo. So let's get this. We have to find electric field, which is close to the voltage over the distance. So the voltage here is 30 kilo. Then the distance between the plate is 0.04 times 10 to the power minus 3. So you can see that with this, meaning just even take 30 divided by 0.04, that alone is given us 750. So you bring this will 10 to the power 6 volts per meter. So this is supposed to be 750 mega volts per meter. So but when you look at the possible answers, we have them expressed in kilo. So if they were expressed in mega, so A should have been the answer. So but mega. Okay. Now moving to question 87. A two-plate capacitor has a charge of 25 coulombs. If the effective area of each plate is 5 centimeters square, find the electric flux density of the electric field. Again, this one is about calculating electric flux density, which is charge over what area, right? Charge over areas. And the charge here is 25. The area, which is given at 5 centimeters square, which is 5 times 10 to the power minus 4. So this become again 10 raised to the power 4 here. 5 will give this will, so this will just be 50 kilo. Remember, this is D rather, okay? D 50 coulombs per meter square. So 50 kilo. So the answer here is B, coulombs per 50 coulombs per meter square. Now question 88. The electric flux density between two plates separated by a mixture of relative permittivity 5 is 2 microcoulombs per meter square. Find the voltage gradient between the two plates. Again, voltage gradient, we are interested in what? The electric field strength, right? So with this question here, you can see that we are given the electric flux density, which is D, is equals to what? It's giving us 2 microcoulomb per meter square, right? Now we are also given from the question the relative permittivity, right? Which is 2. No, relative permittivity here is giving us 5 rather. Okay, we get 5. Now we are asked to find the electric field strength, which is the voltage gradient. We know that the electric electric flux density over the electric field strength will give you what? The absolute permittivity of what? Absolute permittivity. So absolute permittivity, which is equal to relative permittivity times permittivity of what? Free space. So we are interested in electric field strength, so we'll make that one the subject. So this becomes electric field strength, which is a potential gradient, or the voltage gradient is going to be equals to electric flux density, then divide by the absolute permittivity. So this becomes 2 times 10 to the power minus 6, then divided by the relative permittivity, which is 5, times the permittivity of free space, which is 8.854 times 10 to the power minus 12. So this will give us 2 times 10 to the power minus 6, right? Divided by 5 times 8.854 times 10 to the power minus 12. Okay. So what do I get for this? So we get 45,177.32 volts per meter. So you can change this to what? To kilo, because looking at the answers again. So in kilo, that would just be 45.18, let's say, kilovolts per meter. So that will correspond to question D. Now 89, the capacitance of a capacitor that's with a dielectric is introduced to it. Yes, so the capacitance is going to increase when you include a dielectric, right, to it. So the answer here is B. Now the last question, which of the following is a correct expression of multi-plate capacitor? What that means is if you have many plates, right, like 5 plates, 10 plates, like the question that we just solved, you can see I even wrote the formula, right? So the formula is going to be what? B. So this is going to be the end of questions for today. We continue later. Bye bye.